Hello, it's your asynchronous lecture, week 3. Today we're going to be talking about section 6.4, which is volume of a solid slicing. So this is going to be a little bit different than what we did in 6.2 and 6.3. We're no longer going to be talking about solids of revolution. We're going to be talking about different types of figures where we're going to look at the volume by making slices into the figure and sort of talking about the geometry of the slice. This, not going to lie, is going to be one of the more challenging sections you're going to do in this class. I mean, all of these applications in chapter 6, I think are definitely more challenging as far as volume is concerned. This one in particular just requires a lot more of you thinking outside the box. So don't despair, however, because it's actually a pretty short section and there's not a whole lot I'm going to be assigning out of here. So my goal right now is to go through 4 examples with you to really give you a good idea of how to do these problems, give you a good solid base. Gosh, sorry, I gotta figure out. Okay. So that's my goal. I'm gonna try to just do 4 examples, get you started in the right direction. And then I'm gonna start 6.5, which you're gonna feel some relief when we start 6.5. So 6.5 is gonna be about arc length and surface area. What I'm planning to do today is just kind of talk about some arc length formulas, and then we'll finish out 6.5 on Wednesday when I see you in person. But I just want to get you started on it today. Yeah, so that's my goal. So yeah, that's what we're gonna do. So 6.4, get started on that as soon as you absolutely possibly can, just because these problems are going to take you some time. For the most part, I'm expecting a pretty eventful office hour on Monday. I actually do hope, because it means that you've been working on things. So let me give you the definition that we're going to be working with in 6.4. And then the definition itself, you're probably going to be like, okay, this seems really straightforward. And then we're really just going to have to build off of that. So volume as an integral of the cross-sectional area, we're going to say, let A of y be the area of the horizontal cross-section. And I do mean area, because we're going to be, thinking about volume in terms of area. We're going to take an area and we're just going to sort of spread it out to create the volume. So we're going to let A of y be the area of the horizontal cross-section. At height y, of a solid body extending from y equals a to y equals b. Then we have the following formula. The integral from a to b of a of y dy is the volume of the solid body. So this all seems really innocent and straightforward. You're going to find that most of the time that you spend working on these problems is just going to be finding that function a of y. Now, depending on the figure, and I'm going to give you a couple different examples where you're going to be looking at your cross-sectional area perpendicular to different axes, this is not always going to be A of y and dy. If we're going to be looking at a cross-section that's perpendicular to the x-axis, then we're going to adjust this so that we have A of x dx. So I don't want you to get stuck on the y notation. This is going to be one of those nights. It's going to be sweater on, sweater off. I'm like, oh, it's driving me crazy. All right. So I'm going to just get started. We're going to jump right into this. I think that's the best way to get going, just to start. So let me give you example 1. Consider the solid whose base is the unit circle x squared plus y squared equals 1. And whose vertical cross sections perpendicular to the x-axis are equilateral triangles. Sorry, I put a period on the sentence too soon. And whose vertical cross sections perpendicular to the x-axis are equilateral triangles. Find the volume of the solid. Now, part of the trickiness here is just being able to visualize the region. Disclaimer, sometimes I'm really, really good, not going to lie, at drawing in 3D, and other times, terrible. And I don't know what tonight's going to be. Is it going to be a good one or a terrible one? I'm going to try to do my best to make some really nice drawings so that you have a really good sense of what's going on. For some of the homework problems that you're going to work on, not very many of them, you're going to be given a figure, but for other ones, you're going to have to kind of draw this out yourself. And you're going to find that sometimes you're going to need more than one view in order to actually get this area function to pop out for you. So we're gonna build this though. All right, so we're talking about a solid whose base is the unit circle x squared plus y squared equals 1. The vertical cross sections perpendicular to the x-axis are equilateral triangles. So you're talking about a solid such that the base is a circle, x squared plus y squared equals 1 is a circle of radius 1. So we're talking about a solid whose base is a circle. I'm just going to do it like a general drawing here, and then we're going to try to formalize it a little bit. And its cross sections are equilateral triangles. So essentially what you're looking at here, I can try to give you a good picture, is you've got, very, very hard to do this. You know what? I'm going to adjust my circle a little bit. Let's imagine here that we have this equilateral triangle, and you've got this sitting on a base that is a circle. I'm kind of looking at it at this angle here. All right, so the base is a circle, And the equilateral triangles are going to be built off that. But imagine, I mean, right at this point, I have the equilateral triangle such that the base of the triangle is the diameter of the circle. But I can scoot that down so that I'm no longer looking actually at the diameter of the circle, and I'm looking at like a chord on the circle. And when I do that, I still get an equilateral triangle. But remember, in an equilateral triangle, all three sides are equal. So I'm going to end up with a triangle that's smaller. And if I do that again, I'm looking at a different chord on this circle. It's an equilateral triangle. Again, I'm looking at a triangle that gets smaller. Now imagine that you're taking that the other direction also. This is going to get harder to see as we start to draw more triangles in here, but you're going to see that's going to continue happening over and over so that you end up getting this shape that looks kind of like that if you can visualize it, but it's going to go back again. It's going to go down again as it heads backwards. It's kind of hard to see that from this visual. So the base is a circle of radius 1. And what this would look like if you looked at it directly from the front is you'd be able to see this point that starts to head upwards to the top. But if you were to actually make a cross section in here, and you can pick out one of the pieces if you want to, I'm going to pick out this one that I drew. What we're really doing when we're doing slicing is we're going to come up with a general formula for the area of a general slice. So it could be any slice that we want, but we're taking a slice of this, finding the area of that. And then when we integrate that, we're really just kind of pulling this backwards. If we talk about integrating this from A to B, we're going from, in this case, it would be like from front to back. So we'd be taking that area, and as it gets larger and then smaller again, that's going to be giving us our volume when we actually apply the integration to it. So if you want to see this on some coordinate axes, I'm going to give you a couple different views. Now, you probably have never drawn anything in 3D before, is my guess. There are a bunch of different ways to do this. There's not necessarily one right way of doing it or one wrong way. It kind of depends on the picture that you're dealing with. I'm going to draw my axis over here off to a little bit of an angle. This is going to be your y-axis. Usually your z-axis is the one that is vertical. Not always, but often. There's your x-axis. And again, you can kind of adjust this to whatever picture that you need. Sometimes you'll find that one angle is better than another, and that's okay. So what I'm going to do is I'm going to draw the base, and I'm going to draw it such that it looks like this circle, x squared plus y squared equals 1. You're going to have a hard time seeing that, though, on this three-dimensional picture because it's very, very hard to draw in 3 dimensions. Now, these are kind of running into each other. But if you think about this in 2 dimensions and then sort of translate this with your mind onto the base, I mean, think about what this circle looks like. Your base, and this axis right here, your 2D coordinate grid, is what would be here on the bottom. So the z-axis would be coming out of the page towards you or back into the page. But you would have the circle of radius 1. It looks like that. All right, so that's your circle. All right, so we're going to move this onto your 3-dimensional drawing, and you're going to do the best you can to make this look good. It's probably not going to look circular, but it doesn't matter. All you're trying to do is just get a general idea for what's happening. And I can already tell that I'm too far back here. You want it to still kind of look circular because you want to get a good idea of what's happening. The better your picture is, the easier it's going to be to work with the data. But, you know, we're limited here because we're not artists. Well, some of you might be, but nobody told me they were an artist when they introduced themselves. Okay, so this is the base that you're looking at right now. And remember that z is the height. So you've got these equilateral triangles that are going upward. So what I try to do is when I'm drawing one of these cross sections, I try to make it so that the base of my cross section is parallel to the axis. Now, looking back to your problem statement, consider the solid whose base is the unit circle x squared plus y squared equals 1, and whose vertical cross sections perpendicular to the x-axis are equilateral triangles. So when we're drawing this perpendicular to the x-axis, we're drawing our triangles such that each triangle is going to be perpendicular to the x-axis. The only way for that to happen is for our triangles to work themselves this way. I'm going to attempt to make these look equilateral over here. It's going to be skewed looking, but hopefully you'll at least get the gist. This is just one of the triangles that you're going to see on this figure. Remember, it's made up of this infinite number of these triangles. But this is how we draw this perpendicular to the x-axis. So it's meeting it at that 90-degree angle. In this case, it would be parallel to the y-axis, perpendicular to x. But you could draw these series of triangles. Again, I'm trying to draw the bases so that they're parallel to the y-axis, and I know it doesn't look like they're perpendicular to the x-axis, but that's just the angle. These really are going to be perpendicular. And just, do the best you can to make them look like beautiful equilateral triangles that have, roughly the same angles on them. Imagine that you had a triangle that was whose base was sitting right here on the y-axis. If you had that situation, you have a triangle coming up like this. So I hope that this is becoming easier to visualize. So the triangle whose base is sitting on the y-axis, that's going to be the tallest one because that's going to be the one with the longest base. As you move backwards now, in the opposite direction on the x-axis, you're moving away from the y-axis, and then you're going to end up in a situation again where your triangles start to get smaller as you head towards the other end of this circle. So if you want to draw those, fine. You don't have to. I really, like I said, just want you to get a general gist here. This one is a much smaller triangle, but what you would see is this figure that looks kind of like that. That's kind of running its way through. So I hope that we can visualize this. I want to focus now, though, on how we're going to actually write the equation for the area. And by the way, I said this earlier, but I don't know how much of it was retained. So I definitely am going to be mentioning this again. We need a formula, A of x, to represent the area of each equilateral triangle. Now, you might be like, well, why do we need a formula for that? We know that the area of a triangle is the base times the height. Yes, but you're dealing with an infinite number of triangles here, and each one of them is going to have a different area. And we need to consider the general formula for the area of the triangle. That's the hard part of this. So let's go ahead and kind of break this down. Your base of your triangle, if you're thinking about this as like, okay, well, I know I'm finding the area of a triangle. I know the area of the triangle is going to be 1/2 the base times the height. Then you're going to need the base and the height. The height we're going to have to come up with. The base we're also going to have to come up with, but we're going to start with the base, though, because that's going to be the part that's a little bit easier to see. Notice that the base of each one of these equilateral triangles is going to be twice the distance from the center. I'm looking at the triangle that's situated right now on the y-axis. The base of this triangle is going to be twice the distance from the center of this base of the triangle to the edge of the base of the triangle. Now, if we're looking at this particular triangle, well, that's no big deal because we know that this is just going to be 1 in this case. If I'm talking about this point right here correlates to this point right there if we're looking at this in the other dimension. You know, you can take this guy, flip it around like that, and now you're looking at the base in 2D. So what we need is a formula for this circle that is written in terms of x, because I need a of x. That means I need a formula such that y equals something that has to do with x, and the base of our triangle is going to be based off of that, because the length of the base is just going to be twice whatever the distance is from the center to the edge. So using your formula, x squared plus y squared equals 1, and you did this a little bit in algebra previously, you can rewrite this as y squared is 1 minus x squared, and then y equals plus or minus the square root of 1 minus x squared. Now, the plus or minus part comes in for representing this as a function. So now we have a function. Before we did not, it did not pass the vertical line test. But the plus or minus allows us to actually graph this in 2 pieces so that each piece on its own does represent a function. The positive piece, y equals plus the square root of 1 minus x squared, is the top of the circle. And like I said, you did this over the years here and there in your algebra classes. But the top piece is y equals the square root of 1 minus x squared. That corresponds then to what's happening over here on this part of the circle. I could be using colors right now. Why am I not using colors? Oh, well. Okay, so this is y equals the square root of 1 minus x squared. That is the function. Once you have the function, well, now we can really start to talk about what's happening with the base of our triangle. So imagine now that the base of your triangle, it's sitting here perpendicular to the x-axis, and it is just kind of controlled by what's happening here on your circle. Think about what you know about equilateral triangles. Put that right there. You might even want another. I want to make another view. All right. Your base is going to be represented by the distance that goes from here to here, or at least half of your base will. The other half of your base is going to be the other side of that. That's really what we're looking at here when we're talking about using this circle to find that value. If you never did this equilateral business in trig, I'm going to write it down right now so that you can see it, and you might be like, this looks familiar. Maybe I remember doing this. Your teacher might have derived special angle trig functions for you using this triangle. I know I did this when I taught trig. Gosh, it's been a while since I've taught trig. But I've done this again for calc students anytime I've had to remind them of how to find specific function values. So imagine that you have an equilateral triangle, and your equilateral triangle is made up of 3 legs that all have the same length. It has to be. That's the very definition of the equilateral triangle. What we're looking for here is going to be represented by half this distance. So if I wanted to think about this triangle in terms of what I have pictured and using my function for the base, I can rewrite this using just half the triangle. Head downward, I guess. Well, no, I'll head to the right. So I'm going to focus now on taking only the right-hand half of this triangle. Now, when I do that, this leg right here doesn't change at all. It's still 2. But my bottom leg of the triangle used to be 2 units long. Well, now that I've chopped it in half, it's only 1 unit long. If you apply the Pythagorean theorem and you solve for the value of your missing leg by taking a squared plus 1 squared equals 2 squared, you'll come up with the square root of 3. This is technically a right angle. So we have that. Now, think about this in terms of your actual region here. If we're trying to come up with a formula for the length of the base of this triangle all the time, remember that the leg length is based off of this function right here. Well, imagine that this triangle right here is the same as half of your equilateral triangle from the picture. Okay, so this triangle matches up with that one. Now I know it's kind of hard to tell because this is in 3D and I drew it by hand, yada, yada. But this length is always going to be represented by the formula, the square root of 1 minus x squared. No matter how I move this, I can shift it forward on the x-axis and bring it towards us. And of course, when I do that, this point along here is going to move down the circle. The triangle will get smaller and smaller and smaller and will eventually go to 0. If I were to move the triangle back towards the origin, again, you're going to see that this point here at the edge of your triangle now is going to move backwards and the triangle is going to get bigger and bigger and bigger. But notice that what's happening with this formula, if I were to have moved the triangle all the way forward as far as it could go, I'd be moving it towards x equals 1. We didn't mark it, but it's officially there because it is a circle of radius 1. Now, note that if x is 1, y is going to be the square root of 1 minus 1 squared, which is 0. And that is indeed the case. Y would be 0 at this point because y is not going anywhere on the y-axis. Y would have to be positive if you were actually heading this direction, but you're not. So you're kind of checking this, again, with the formula to make sure that this makes sense. If you were to move your triangle backwards towards the origin, in that case, if you moved all the way to the origin, x would be 0. Well, if x is 0, then y in this case would be the square root of 1 minus 0 squared, which is 1. And indeed, if you move this all the way back, when the x value goes all the way to 0, well, now you're sitting at this point, x is 0, y is 1, which is represented by this point right here. So you can go ahead now and say that this triangle right here has to represent the dimensions for what's going on with this triangle over here. But we're just going to generalize it using this formula. I know that half of this base, the half that's on this side, is controlled by the square root of 1 minus x squared. So I'm going to rewrite my triangle one more time. And instead of letting this value be 1, I'm going to multiply each leg of this triangle by the square root of 1 minus x squared. And as long as I multiply each leg by the same quantity, then I haven't actually changed the triangle at all. Every leg just got multiplied by the square root of 1 minus x squared. And the only reason I did that is because I just knew that half of the base has to be controlled by this formula. So I just multiplied this out because I already had a 1 here. So 1 times the square root of 1 minus x squared is still just the square root of 1 minus x squared. But now we have a formula not only for the base of the triangle, but also for the height of the triangle. So I know that the height of the triangle is always going to be the square root of 3 times the square root of 1 minus x squared. And now I can actually write the formula for the area. So I can say now that the area of my triangle is 1/2 times the base times the height. The base, we know, is going to be twice this quantity, because if I use the square root of 1 minus x squared, that's only this side of the base, just half of the base. But now I have to multiply it by 2 because I need the other half of the base of the triangle. So I'm going to say twice the square root of 1 minus x squared for the base. And then for the height, well, I know the height of the equilateral triangle is going to be the square root of 3 times the square root of 1 minus x squared. See what I mean? This is tricky. When you actually get all these to work out for you, it's very nice. You'll find it's extremely rewarding, but some of them are going to take more work than others, and some of them will take quite a bit of work. This is the hard part. Once you have this, no big deal. You're just going to simplify and integrate. So 1/2 times 2 just gives you 1. So I just have the square root of 3 times the square root of 1 minus x squared squared. So that just leaves me with 1 minus x squared. So now we'll go back to our formula. We're looking at the x integral because I have an a of x, and I'm going to go from a to b. So now you need to figure out your limits of integration. I know that I'm looking at the whole entire base being the circle, x squared plus y squared equals 1. So that means that when I integrate this, I'm looking at what occurs on the x-axis. And I know that my circle, and again, we can look at this two-dimensionally and sort of transfer that over here. If the x-axis here is going from -1 to 1, then over here, I'm also going from -1 to 1. So if I'm looking at what's happening on the x-axis and I have an a of x, then my limits of integration also have to correspond to the x-axis and where this region lies. I know that my region lies between -1 and +1 on the x-axis. Now, do pay attention, because every once in a while you're going to get an exercise that specifies that, like, maybe this is only happening in quadrant 1, or maybe it's only happening for values between 0 and 1, or positive values of x or something. So make sure you're paying attention to that. But for our purposes, we are going to integrate from -1 to +1 because that's where our region lies on the x-axis. And then I'm going to integrate a of x dx. I'm going to pull the square root of 3 out. When I integrate 1 minus x squared, I'm going to get x minus 1/3 x cubed. And I'm going to take this from -1 to +1. So we have the square root of 3 times 1 minus 1/3 times 1 cubed is still the same, minus, and then -1 minus 1/3 times -1, because -1 cubed is still negative. And then we'll simplify. 1 minus 1/3 is 2/3, and then minus, and be careful with all your signs here. This is going to be -1 plus 1/3, which is -2/3. So not the end of the world, but I mean, you don't want to end up accidentally missing your sign and saying, wait, 2/3 minus 2/3 is 0, therefore my volume is 0, and then you're going to be in a big mess. 2/3 plus 2/3 is 4/3. So officially your answer is 4 times the square root of 3/3. And it is officially units cubed because it's volume, but I'm not going to require you to write that. That's implied. So that was your first example. So you're going to see at least 1 or 2 on your homework where the base of your region is a circle. It might just be 1. But what's going to happen is when you see this on your homework, I believe you're going to look at a base being a circle and the cross section, it looks like will be a square. Or maybe, oh yeah, and you also have one where you have an isosceles right triangle. So, so yeah, there'll be 2 of those. So if your cross section was a square, that's actually a little bit easier for you because you're still going to be basing everything off of this formula. But if your cross section is a square, then you just have that the base of your square is twice the square root of 1 minus x squared. And you know that the area of a square is just the side squared. So it'll be much more straightforward for you to get that area. The equilateral triangle ones, and you're going to see more than one of these, but they're all going to work the same way. So now that you've seen this built up, you can work on those equilateral triangle ones. The equilateral triangle ones are harder, but they're all going to use the same idea. For the squares, like I said, they're easier just because in this case, the area of a square is just side squared. But I mean, once you do this once, doing it again is probably not going to be that big of a deal. So yeah, you'll do equilateral triangles, squares. What else did they do in here? Semicircles. And I think, yeah, I've got a semicircle example I'm going to show you. So no big deal there. Okay, so let's do another one because obviously we all are just really anxious to know what is going to happen next. Let's see. Oh, there we go. Mm-hmm. Get you another example. Oh yeah, my semicircles are coming up now. Excellent. All right, example 2. We are going to find the volume of the solid. You might actually find that example 1 might have been one of the harder ones that we're going to do today. That's actually kind of good. Find the volume of the solid whose base is the triangle enclosed by x plus y equals 1. The x-axis and the y-axis. The cross sections perpendicular to the y-axis are semicircles. Okay, and again, we're going to draw this out in 3 dimensions, see if we can get it to look good. This one's going to be a little bit easier to draw just because the base is not circular. Anytime the base is circular, it's kind of a pain. Okay, wonderful. You might find it helpful to do a 2D variation of this just by looking at the triangle enclosed by x plus y equals 1. So if you want to do that first, that's fine too. X plus y equals 1 can be written as y equals negative x plus 1. So you've got a y-intercept at 1, and the slope is -1. You could also think about this in terms of intercepts. If y is 0, x is 1. If x is 0, y is 1. Would be those points. All right, so this is the region that you're looking at. This is going to be the base of your figure. So if the base is this triangle, let's go ahead and shift this over to a 3-dimensional drawing. Here's your z-axis. And maybe send it off like this. And maybe send it off like that. Y and X. Try to make this look good. And by the way, I didn't mention this before. If you're not used to 3-dimensional drawing, I know this seems kind of weird because it looks like it's heading down. And usually when we think down, we think negative. But what you want to think about is it's heading towards you, not away from you. And if it's heading towards you, it's positive. So this is actually the positive x-axis. And same idea with y. It's heading off to the right. So we think about that as being positive. If it's heading away from us, like what's happening back here, that's the negative x-axis. If it's going off to the left, that's your negative y-axis. And like I said, you can relabel the axes however you want. They don't have to be here. This is just pretty standard. Okay, so +1 on the y-axis, +1 on the x-axis is going to look like kind of like that. So you've got a triangular base. Oh no. Okay, I have to fix that or it's going to drive me crazy. There's like a mental skill to this where you're like always looking at your destination, not the line you're drawing. All right, so this is the base of your region. Now, it's part of the problem here is making sure that we understand where the cross sections are actually occurring, because depending on where they're occurring, sometimes you're going to get a different volume because your figure is going to look very different. So I'm going to go back to the problem statement. Find the volume of the solid whose base is the triangle enclosed by x plus y equals 1, the x-axis, and the y-axis. So I'm not including anything else out here on this line. I'm cutting this off at the x-axis and the y-axis. There's my base. I'm not going to fill it in because I'm going to end up putting some semicircles on this. Okay, so here's what's key. The cross sections perpendicular to the y-axis are semicircles. So perpendicular to the y-axis, in this case means they're going to be parallel to the x-axis. Perpendicular to y means I'm kind of like dropping them down and chopping off the y-axis with them. So sorry, I know it's kind of hard to see that. If I had, oh, I do have a Post-it note. Let's say if I only had a small, tiny piece of paper, maybe that would help. Oh, these are so sticky. Okay. So when you're thinking about perpendicular to the y-axis, you're kind of thinking about it like this. So in our case, it's going to be parallel to x, perpendicular to y. Sorry, I'm like, my camera has to orient upside down, so it's hard for me to see sometimes. Perpendicular to y just means that I'm kind of cutting through. I'm cutting on the y-axis. I'm not cutting on the x-axis. So if I was perpendicular to the x-axis, in that case, I would be doing something like this. I'd be going slice, 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 but I'm not. Perpendicular to the y-axis means I'm going slice, slice, slice. I'm slicing up the y-axis volume by slicing, as displayed by a Post-it note. Okay, so if my cross sections perpendicular to the y-axis are semicircles, well, imagine here, and I'm going to, again, try to draw this base parallel to the x-axis. I'm already doing a terrible job. I should have drawn it closer maybe, but okay, something like that. So imagine that you have all these cross sections that are semicircles. This would be the base of the semicircle, each one of these. So notice that the semicircle would keep getting larger as you move your way towards the origin. We'll try to make this look like a semicircle. Moment of truth. All right. Pretty pleased with that. And then we'll draw more semicircles. We'll try to give them the same general shape so they kind of look like they're all doing the same thing. Oh no, I'm failing miserably now. Okay. But you can kind of see how these are built now as they're heading upward. Maybe I could fit in one more of these and just kind of fill in that gap. Oh, I want to make more now. Okay. But hopefully you can get a good idea now of what's happening with this region. I don't know if you want to try to make a little teeny tiny one, kind of look like that. Can do that. Mine kind of just the way it looks with the axes, it almost looks like it swings on a curve, but it does not. The way these semicircles go, it should be a pretty straight line from the bottom to the top. So if I tried to draw it, it would probably clash with my axes. So I'm not going to try it. Gosh, if I actually like erased this and redrew it, now that I know what I'm going for, I'd have a little bit of a better picture. Sometimes it's almost like you should draw it and then redraw it once you really figure out what's happening. But this is essentially what's going on. So you've got this solid, the base is a triangle, and its cross sections are semicircles. So you can pick out one if you'd like and just focus on it. Focus on the semicircle. Kind of like that. Okay. Now I can see that this one should have gone out more, but that's okay. What are you going to do? All right. I gave you a formula, or I actually gave you a function, x plus y equals 1. Now the cross sections are perpendicular to y. What that means is I'm going to need a dy integral. So perpendicular to y means I need a of y and a dy integral. So it's really important to even just understand what it is that we need before we start trying to put all this together. Okay, and remember, we're talking about a of y, where a of y is just a general formula for the area of your semicircle. So it might be good to at least just talk about the area of a semicircle. Remember that a semicircle by definition is just half of a circle. The area of a circle is pi r squared. So the area of a semicircle is going to be 1/2 pi r squared. So what you really need here is the r. Once you have r, well, that's going to give you the whole formula that you need for your area of the semicircle. Then you can just simplify and pop it into your integral and you'll be done. So the radius of your semicircle, think about it like that. Looking at this picture right here, is going to be based off this formula that we already have. So the radius, wait, need to go back to this idea. We need an a of y and we need a dy integral. What that means is I need to think about this function, not in terms of x, but in terms of y this time. So we already solved it for y just to graph it. But if you're going to solve it for x, you can do that just by subtracting y. So if y equals negative x plus 1, then x is just going to be negative y plus 1, or you can think about it as 1 minus y if you are more inclined to write this as a subtraction. So we know that this line is x equals 1 minus y. That's our line. And I know that my radius for the semicircle is just going to be half of that x value. Because if you think about this as like how long is x, or how far back do I have to go to get to the x value, your x value is just whatever value you are on this line when you get to the diameter of your circle, the full diameter. So if you're only looking for the radius, you're only going halfway there. So if you think about your diameter as being the x value you attain here, the radius is half that value. I'm going to write that down. So the radius is going to be 1/2 of that value, 1 minus y. I think I was going to say something else about another way to look at that. Oh, no, what I was going to say was, you know how we've been sort of writing formulas and then just eyeballing them and checking them to make sure that they make sense. You can do the same thing here if you need to. So if you think about, for instance, what happens when y equals 1, well, y equals 1 is going to be right here. Remember, y equals 1 actually corresponds to this point on the y-axis. So if y is 1, then x is 1 minus 1, which is 0. Well, that's true because I'm not going out on the x-axis in this case. X is 0. True. And then the radius of this semicircle would be 0. Well, if you move your way towards smaller values of y, you can even think about, for instance, what happens when y is 1/2. Well, if y is 1/2, then x is 1/2. So y is 1/2 would maybe be like right here. X is 1/2 would be like half that distance. So you'd be sitting on this line. And then half of that would be the value for your radius. So you can kind of play around with those numbers and make sure that this makes sense. But your full circle, the full diameter goes out to x equals 1 minus y, whatever that x value happens to be. And then half that distance is your radius. I think part of what gives students a hard time here is just the fact that you're coming up with a general formula. I mean, we can easily come up with formulas for areas of circles as long as you know what the radius is, but coming up with a general formula for the radius is a little bit harder. It is as soon as my air conditioning turns on. That's the problem over here. All right. But now we have a radius, and I know that the area of a semicircle is 1/2 pi r squared. So we can go ahead now and take r squared. R squared is going to be 1/2 squared times 1 minus y quantity squared. Now, it's kind of up to you if you want to leave this as a quantity squared or if you want to actually multiply it out. This would require a slight u substitution when you integrate it, so I might just multiply mine out. So r squared is going to be 1/4 times 1 minus 2y plus y squared. That's what you get when you multiply 1 minus y by itself. So 1 minus y times 1 minus y is 1 minus y is minus 2y, and then plus y squared. Okay, so let's start to set up this integral. So the volume is the integral from a to b, we'll discuss that in a second, of our area. Oh gosh, you know what? I never actually wrote our area. I just found r. So we'll simplify the area before we put it into the formula. So a of y is going to be 1/2 times pi times r squared. So that's 1/4, and then 1 minus 2y plus y squared. So 1/2 pi r squared. And then we'll simplify that one more time. So that's pi over 8 times 1 minus 2y plus y squared. And then thinking about the limits of integration here for our integral, we know that the volume is going to be, you can leave the constant pi over 8 in front of your integral. We're going from y equals a to y equals b. Well, our region exists from y equals 0, which is down here on the x-axis, all the way up to y equals 1. So our region stops at y equals 1. So we're going to go from 0 to 1. And our integrand is 1 minus 2y plus y squared dy. And at this point, no big deal. We're just going to integrate and simplify and we'll be done. So we have pi over 8 times y minus y squared plus 1/3 y cubed from 0 to 1. Now the lower limit of integration in this case is 0, and in this case 0, 0, 0, you don't need to worry about in this particular integral. So we'll have 1 minus 1 plus 1/3, which ends up giving you pi over 24. So that was an example using semicircles. You're going to see some of that on the very few homework problems that I possibly have to assign to you here. Now I'm going to do one with squares. And we'll switch up the base a little bit. Not a ton. We'll do another circular base. Wait, you know what? I don't want to do another circular base. We just spent all this time doing a circular base, and I explained to you what to do when your cross section was a square. I think you'll be okay on that one. This is basically would be like a repeat of example 1. So let's just do one more where we change the function a little bit. But you'll still, well, you'll actually be looking at, I'll give it away, rectangles. So similar to squares, slightly harder than squares, just because rectangles don't have the same base and height. Example 3. So we'll just do example 3, and I feel like that should, that should really prep you about as well as I can prep you for your homework without actually doing your homework for you. But definitely give yourself some time to get through the homework because it's going to take some time. Who knows? Maybe it's going to go way more smoothly than I anticipate, but it's challenging stuff. Find the volume of the solid whose base is the region enclosed by y equals x squared and y equals 3. The cross section's perpendicular to the y-axis. Are rectangles of height, wait for it, y cubed. So we're going to look at 2 different functions working together here. And I'm going to really try to make my drawing as spot on as possible. All right, so the base is the region enclosed by y equals x squared and y equals 3. Again, if it helps you to draw this in 2D first, do it. You certainly don't have to. All right, so 1, 1, 2, 4, 5, 6, 7, 8, 9, 3, 9. And it's not just half of the parabola, it's the whole thing. Oh, y equals 3. Sorry, I was looking at x equals 3. 1, 2, 3. Y equals 3 is right there. Like that. Okay, so this is the base that we're going to be looking for. And we're just going to translate this into 3 dimensions. So what we're going to do when we translate this into 3 dimensions is we're kind of just visualizing this flipping over. I know it's kind of hard to think about it that way, but flipping over onto its side. Or if you want to kind of think about it as you're looking down on it and kind of just rotating it around. Okay, so there's that. With the y, angle it down a little bit more. X, something like that. Z. We will just do the best we can to make this look beautiful. Y equals x squared. And again, kind of goes like that. Now you're looking at this parabola with the vertex at the origin. I've got points at 1, 1, and you know, this obviously does not have to be, you know, drawn out. You can just sort of make a parabola without having to put points on it. That's going to be challenging. 1, 2, 3, 4. I mean, I'm going to try to do that just so it looks nice. I do the best I can for you guys. Okay, so here's your parabola. Kind of like that. And I went up to 4, but officially it's 3. Remember, anytime you're drawing here, you're trying to make it parallel to whatever axis is parallel. So try to make your line parallel to the x-axis. This is your base. If you want to even get rid of the rest of this parabola, you can, because officially this leg is not doing anything for you, and neither is this one. All you're looking at is the region that's between the parabola and y equals 3. Anything else is just fluff. I'm going to keep it though, just because I want to label it, and I don't want to just label just hunks of graph. This is y equals x squared. However, I said in the problem statement that the cross sections are perpendicular to the y-axis. And if we're talking about cross sections perpendicular to y, I am going to want to have everything written in terms of y. So that means I'm going to need perpendicular to the y-axis. That means I'm going to need a of y, and I'm going to need a dy integral. So you might as well just right off the bat think about this instead as x equals the square root of y. I mean, I just labeled them in different spots. It's the same graph regardless. Okay. So here's the trickier part. And I might have made my drawing too small. I know it's always, like I said, you draw it and then you're like, I could see this better if I did this to it or did that to it. The cross sections are rectangles of height y cubed. So if that seems odd to you, well, first of all, they're perpendicular to the y-axis. So you know right away that their bases are going to be down here. The bases of these rectangles. But the height of the rectangle is going to be controlled by y cubed. Well, if y is 1, y cubed is also 1 because it's 1 cubed. So your height is going to start out smaller here. And this is going to be much harder to draw. So I'm going to wait here until I get over here to 3. If y is 2, 2 cubed is 8. So and I'm going to be going from 1 up to 8. And then if y is 3, 3 cubed is 27. So you can see that these are going to go up pretty rapidly. Now, you know what the cubic function looks like. And you might even think about this. Let's see. Do another side view here. Instead of thinking about this in terms of y and x, maybe think about it in terms of y and z. Remember, the height of your function is going to work with this z-axis. If we're talking about y cubed, well, 1, 2, 3. Remember, you've got a point here at 1, 1. You've got a point at 2, 8, and then you've got another one at 3, 27. So your side view actually looks kind of like that. Now, if I were to draw the whole cubic function, it would do something like this. But we don't need the whole cubic function because we're just focusing on the height of these rectangles. There's nothing that's happening below. But this would be kind of like a side view. So the side that we'd be looking at when we look at this view, this is your z-axis, this is your y-axis. It's kind of like you're sitting here at x and you're just like staring down the x-axis towards your figure. That's what this is. This is your side view. So you can see now what's happening on the side. This should be at 327, but the height of these rectangles is going to increase very rapidly. Now, obviously, I cannot properly scale this out because I have this marked as 3. If I mark this as 3, I'm never going to get up to 27. But you can get a general idea of what is going on here, and that's what we're going to try to do. So let's see. I know that the sides are going to be rectangles. I know their height y cubed. So I know that if I'm sitting at y equals 3, the height of the rectangle is going to be 27. So it's going to go up and up and up and up very, very high. And again, like I said, it's not going to be to scale. I just want you to get a general gist of what is happening here to these rectangles. As soon as you lose your parallelness, things start to rapidly deteriorate. Okay. So this would be the height, or this would be the rectangle that you would see if you were looking at what happens at 3. But then if I were to go to 8, 8 is, you know, like a third of that distance, not even. So I'm just going to try to represent this as going up, but not too far. Maybe something like that. And then this one at 1 is going to be a very short one. So short that you're not going to be able to really even visualize it. Okay, so you can kind of see now if you were to connect these with that cubic function, kind of does something like this. And sometimes you kind of have to stare at this, look away, and look again. And then once you see it, you can't really unsee it. Like it just is. Well, part of the problem is this thing is not as parallel as it should be. I know I'm getting really hung up on this parallelness, but for good reason. Okay. So you can start to see now how this figure is coming together. I'm just going to highlight one of these cross sections, just the one that I pulled off of 2. And if you want, feel free to draw more. If sometimes having more cross sections complicates things and it makes it harder to see. Sometimes it makes it easier to see. So imagine if you drew one here, halfway in between 2 and 3. You would be going right about up to this curve. And try to make this parallel as possible. And kind of go like that. But you can see how, if you were to think about this using that concept of slicing, my post-it note going again. You're slicing perpendicular to the y-axis, and each time you slice this, you slice it down, you're creating this rectangle. Now, kind of depending on where you are, at some point you're going to end up hitting a square, but in general, you're going to have these rectangles. Up here, the height's going to be much greater than the width, but as you get down to these super small values, you're going to find that that's going to be the opposite. But yeah, so that's what's happening with your figure. From the side view, if you were looking at these slices, the slices we created are these. So you're slicing it, you're seeing it from the side as like, okay, we sliced down, 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 perpendicular to y. And what you did then was you created these rectangles. And of course, the larger the value of y, the higher that rectangle is going to go, because you're dealing with the cubic function here. Okay. So let's build up our formula for the area of your rectangle, a of y. So the area of a rectangle is the base times the height. Now, personally, I feel like once you start to do these and you see a couple of examples, I do think that even though it's kind of slow going, it starts to catch, and then you start to get a good sense of how to build these formulas. But I mean, think about this cross section here that I shaded in. We're talking about a rectangle, and the base of the rectangle is going to be twice the distance from the y-axis up into this point. Now, the distance from the y-axis up into this point is always going to be x equals the square root of y. So it must be the case that the base of my rectangle is twice the square root of y. Okay, so remember, it's the square root of y because the distance from the y-axis to any point on this curve is the square root of y. And I also have to think about the other side of the base. So the base is made up of, this entire parabola, not just the one side of the parabola. All right, so one side is the square root of y, the other side is also the square root of y. You can use symmetry there. And then the height, well, I already gave you the function for the height. The height of your rectangle is always going to be based off of y cubed. So even this one, even though this one seems like it's a lot crazier, it's really either not too bad, or you just get to the point where you're like, okay, I'm starting to see how this works now. Starting to get a sense of how to put these things together. And now we can go ahead and multiply these out. 3½ is 7/2. So your area is 2y to the 7/2 power. And now you just need to set up a formula for your volume. Your integral is going to be with respect to y. So you need to look at where the region exists on the y-axis. It starts here at y equals 0, and we cut it off at 3. That's what we were told in the problem statement. So we're going to go from 0 to 3. And then we're going to integrate the area. with respect to y. 7 halves plus 1 is 9 halves. We have 2 ninths. Y to the 9 halves from 0 to 3. And then we have 4 ninths times 3 to the 9 halves. And then 0 to the 9 halves is going to be 0. So that's 4 ninths times 3 to the 4.5. I don't know. 3 to the 4 is 81. 81 times 4 is 324, and then ninths times the square root of 3. And that simplifies down to 36 times the square root of 3. Oh my gosh, you guys, I have this awful confession to make, and it's that I have no idea what time I started this recording. No idea. I want to say I'm at like the 90-minute mark, and I don't see how that's possible because I've only done 3 examples. This is not good. I'm trying to think, like, is there a way for me to figure this out? Like, what was I doing when I signed on to this meeting? What time was it? I don't know. All right, that was the last example I was going to show you from 6-2. I really feel like I still have like a good solid 40 minutes left, so I'm going to take it. I need to make a note to self, though, to at least just note that for the future. Okay. Yeah, I think I have a solid 40 minutes left. Sorry, but I remember looking at the clock before like 15 minutes before I started, I think. Okay. I'm going to do that. All right, so that was volume of a solid by slicing. So again, you're focusing on what's the base region, building your geometric formula for your cross section off of that base. So we went through a couple of examples here. Like I said, you're going to see an example on your homework where your base is a circle or maybe even a semicircle, but the example that I gave you was a circle. And it was the full circle. You might occasionally see that you're only given like quadrant 1 or something. That's fine. Even if you were only given quadrant 1 in this case, it still is going to work off this formula. That would just affect your limits of integration if that were to be done. So we talked about cross sections possibly being equilateral triangles, which is something that you're going to see on your homework. We talked about circular bases. We talked about triangular bases and cross sections that are semicircles. So you're going to see semicircular cross sections on your homework also. And then we talked about just bases that were based off different functions, which you're also going to see on your homework. And your homework is going to do something like that with the base, where it's going to base it off of particular functions. And then you're going to be given different types of cross sections to work with on that particular base. So yeah, it should be good. Like I said, this can be really challenging, but hopefully having worked through these 3 examples, you've seen a lot of the different things that you need to think about as you kind of build up the formulas for the areas of your cross sections. Just remember, if you're perpendicular to the y-axis, integrate with respect to y, perpendicular with respect to the x-axis, integrate with respect to x, build your a of x, so on and so forth. So make sure you're paying attention to little things like that. Is key. And because it's, you're doing your homework on Achieve, and you're not going to know if, let's say your area function was correct, but maybe your limits of integration weren't right and everything is wrong and you can't figure out why. It could be any number of things. So make sure that you're paying attention to the little pieces, make sure you understand the boundaries so that your limits of integration are correct. Okay, now, like I said, when we get into 6.5, you're going to be breathing a sigh of relief. Because 6.5 is based off of formulas. And yes, there is some integration that you have to do in 6.5, but honestly, that's the only thing that you're really going to need to worry about here. Otherwise, you're just going to be focusing on formulas. And a lot of these are going to be really basic integrals. Some of them you're going to use certain integration techniques that I'm going to show you in some examples. So it's not like, oh my gosh, I don't know what to do. It will not be that situation because I'm going to show you the integration techniques that you're going to need here in 6.5. So 6.5 talks about two different things. One of them is arc length, the other is surface area. I'm going to focus right now on arc length. We'll talk about surface area in class on Wednesday. So this is 6.5, arc length. Surface area of a solid of revolution. You guys know what arc length is. You talked briefly about arc length when you were in trig, but when you were in trig, you used the formula S equals R theta. So usually when we talk about arc length, we use a little s or a lowercase s to denote that. We're not going to be talking about it in terms of angles in this class. That doesn't make any sense, but I'm going to give you an arc length formula. Suppose a function y equals f of x is continuous on the closed interval from a to b and has a derivative that's continuous on an interval containing a and b. That's something that gets overlooked a lot. I'm going to try to point that out when I go through my examples. Just make sure that when you take the derivative, that your derivative is actually defined in the interval that you're given. The arc length S of the graph is given by from x equals a to x equals b. So here's your formula. The integral from a to b times the square root of 1 plus f prime of x quantity squared dx. Now this formula will also work if you integrate with respect to y. So if you're given a function that's written as x equals instead of y equals, it's going to work the exact same way. I'm going to show you an example of that, but I'm not going to bother rewriting the formula. It's the same thing. Example 1, find the arc length of the curve y equals 2x to the 3/2 power on the interval from 0 to 6. Sorry, I'm trying not to yawn. I'm always so tired. You would think that the adrenaline of all the exciting calculus work would make me not so tired. But now that we're done with the exciting stuff, I'm yawning. Sorry. Okay. We're going to just follow the formula here. So build this from the inside out. Start with taking f prime, then square it, then add 1 to it, then square root the quantity. So the problem with the integration a lot of times is going to come with the square root, but we're going to cross that bridge when we come to it. So let's start by taking y prime. I'm just labeling these because it's the first example, and I figure I would just write the steps down. Y prime, I know it's been a while since we've taken derivatives for some of us. You're going to bring the power out front and decrease the exponent by 1. So this is going to be 3. If you want to write it as 3 times the square root of x, that's fine. If you want to write it as 3 times x to the 1/2, that's fine too. The only reason I wrote it like this is because we're going to end up squaring this quantity. And I just figure you square a square root, that's a little bit more of straightforward, but it does not matter. Y prime squared is equal to 3 times the square root of x squared. So that's 9. And then the square root of x squared is x. And then you're going to add 1 to that to meet this part of the formula. So 1 plus f prime of x squared is 1 plus 9x. And then you're going to put it into the integral. We're going from a to b, so we're going to go from 0 to 6. And we're going to take the square root, don't forget to square root it, of this quantity, 1 plus f prime squared. Now, if it's been a while since you've integrated this type of thing, this is a u substitution, where u is going to be the integrand, 1 plus 9x. du is 9 dx. Well, you don't have 9 dx, you just have dx. So divide that 9 out on both sides, and that will give you your dx. Now, I'm going to switch my upper and lower limits of integration. Like if you took my Calc 1 class, I taught you how to do this. You don't have to do it. You can always back substitute. But if I know that x is 0 and x is 6, those are my limits of integration. I'm going to switch those over to u limits so I don't have to back substitute. Well, I know that u is 1 plus 9x. So u is 1 plus 9x. 1 plus 9 times 6, which is 55, or 1 plus 9 times 0, which is 1. So those are my new limits of integration. So I'm going to rewrite this integral. I'm going to send it from 1 to 55. And this is going to be the square root of u. And then dx is represented by 1/9 du. Now, of course, the square root of u is u to the 1/2. I feel like we should be pretty comfortable with that at this point. So if we have u to the 1/2 and we're integrating, increase the power by 1, divide by the new exponent. So we'll multiply by 2/3. You'll have u to the 3/2. And now that you have a u integral with u limits, you can just apply the FTC directly. If you did not switch your limits of integration, then you'll have to back substitute for x and use the original x values, 0 and 6. So I have 2 27s, and then I have 55 to the 3/2 minus 1 to the 3/2. Now, what you're going to find is for a lot of these exercises, they're not going to simplify very nicely. So I don't want you to feel like, oh my gosh, like I have to either give a decimal approximation, which I never, ever, ever want. I don't want a decimal approximation ever. I always want it exact. But if you want to write this instead of as 55 to the 3 halves, as 55 times the square root of 55, be my guest. I would like to see you simplify the 1 to the 3 halves as just 1. If you want to distribute the 2/27ths, fine. But really, it's not going to get much better than this. The square root of 55 can't be simplified by pulling out a perfect square factor. Stick a fork in it, it's done. That wasn't so bad, right? Of course it wasn't. All right, let's see. Let us do another one. Now, the next example I'm going to show you, find it. This is one that students tend to have a harder time actually integrating. So it's the setup it's not a big deal. And this is the opposite of what we dealt with volume. With a lot of the volume problems, once you set it up, it wasn't that hard to integrate. This is the opposite here in 6-5. Some of these are going to be easy to integrate, but not all of them. This is one that's going to require a little bit more ingenuity. So I'm going to show you how to do this, for example, 2. So we're going to find the arc length. For y equals 3 halves x to the 2/3 plus 4 on the interval from 1 to 27. Okay. Excellent. Remember, first we're taking the derivative, then we're going to square it, then we're going to add 1, then we're going to take the square root, and then we're going to see what we have left and figure out if we can integrate it. So the derivative is y prime. Bring the exponent out front and decrease the exponent by 1. 2/3 minus 1 is negative 1/3. The derivative of 4 is 0, so don't rewrite your 4. The derivative there is 0. Okay, so the 2/3 and the 3 halves, those multiply together to give you 6/6, which is 1. So y prime is just x to the negative 1/3, or 1 over x to the positive 1/3, if you want to write it like that. It's kind of up to you. The next thing you're going to do is take y prime and square it. So y prime squared is 1 over x to the 1/3 squared. And there are a number of ways in which you can simplify this exponential expression. You can distribute the exponent. That might be the easiest way to see this. There's an exponent rule called quotient to a power, and that allows you to distribute a power into the numerator and denominator of your quotient. Oh my gosh, my leg just fell asleep. Hold on. Yikes. Okay. It's very painful. I'm going to simplify this now. 1 squared is just 1. In the denominator, remember when you take a power to a power, you multiply the powers. So 1/3 times 2, 2/3. Looks like that. Okay, now you're going to add 1 to it as part of the formula. So this is 1 over x to the 2/3 plus 1. If you want to leave it like that, fine. You will find in a minute that you're going to have to work with that a little bit. But you know what? Sometimes when we first see things, we don't really know quite what we're getting into yet. And you're not going to be sure until you start to actually put the integral together. So your integral is going to go from 1 to 27. Don't forget to take the square root, because sometimes students are just like, oh yeah, no big deal, and they integrate it and they forget to square root it. And that's usually where the complications occur, is with the radical. Oh, by the way, I mentioned that I was going to try to bring this up with each example, and I forgot for the first example, and I almost forgot for the second one. Remember when I gave you the definitions of arc length? We said that the function has a derivative that's continuous on an interval containing a and b. That's definitely something you're going to want to check just to make sure that you can actually use this formula. Notice that this derivative is going to exist for any value of x as long as x isn't 0. We just can't divide by 0. But 0 is not in the given interval, so you're okay. You don't need to worry about it. If 0 was in the given interval, we would need to rewrite this function to be in terms of y instead of x. But I don't think you'll have to worry about that in this homework set. All right, so you're looking at this, and then you're like, how would I integrate this? I don't know. And if you tried to do a u substitution, you'd end up in a big mess, because you'd let u be 1 over x to the 2/3 plus 1. You would take the derivative, and you'd realize you don't have anything else with an x in it sitting out here. So what you're going to do is you're going to take this radical, and you are going to rewrite your expression as one fraction. So I'm going to write this as 1 over x to the 2/3 plus x to the 2/3 over x to the 2/3. I'm going to do this in pieces for you guys, but you clearly wouldn't need to show me that much work. I just want to make sure it's clear. Now you have a common denominator. You can add those up as just x to the 2/3, and in the numerator, you have 1 plus x to the 2/3. And this whole quantity is under the radical, so make sure that you can clearly see that. Otherwise, you might mistake that in your work and just run along assuming that your denominator is something other than what it actually is. Okay, so you're wondering, how did this help me? Well, I'm going to show you. X to the 2/3, and I know we're not used to thinking about it like this, but remember, x to the 2/3 is actually a perfect square. Look at that. We got x to the 2/3 by squaring a quantity. This is a perfect square. If I take the square root of a perfect square, then I'm just going to get the original quantity back. So what you can do here is you can split up your radical. You can take the radical of a quotient and split it up into the quotient of two radicals. And if you want, instead of writing it as a square root in the denominator, you can write it as a 1/2 power. You don't have to. I just think that might make it a little bit easier to see. The reason I want to keep the numerator in the radical form is because we're going to use another u substitution, and I think it's going to be easier to see if you keep that radical in the numerator. Oh, I almost forgot my dx. Yikes. Okay. When you take a power to a power, you multiply the powers. 2/3 times 1/2 is 1/3. So you're going to end up getting that original 1/3 back in the denominator. So you have this situation now. And again, you might be wondering still, like, okay, I still don't know what to do with this integral. Well, the nice thing is that now when you go to use a u substitution, you have another x quantity out here. You don't just have dx, but you have some other function of x in there that's going to help you account for that missing derivative. So we're going to let u be the radicand, 1 plus x to the 2/3 power. And then du is going to be 2/3 x to the negative 1/3 dx. Now this is good because you actually have part of this in here already. If you need to make it clearer, multiply both sides by 3/2 to get rid of this 2/3, or divide it by 2/3, which is the same as multiplying by 3/2. Rewrite this now as x to the 1/3 in the denominator, dx. Okay. That's exactly what you have here. In the denominator, you have x to the 1/3, and then you have this dx off to the side. So we can go ahead and rewrite our integral. I'm going to also switch out these limits of integration. If you're not sure what to do first, start to piece this integral back together first. That's the main important thing. So 3/2 du is equal to 1 over x to the 1/3 dx. And then you have in the numerator just the square root of u. And then we're going to rewrite our limits of integration to match the variable. Right now they're x limits. We're going to rewrite these over to u limits. So if we have x is 27 and x is 1, well, we'll find those corresponding u values. U is 1 plus x to the 2/3. I'm doing this for 1 first just because it's a little bit easier. 1 to the 2/3 is 1. 1 plus 1 is 2. That's going to be your new lower limit. Now, 27 to the 2/3 is just 27 to the 1/3 squared. 27 to the 1/3 is 3. Square it, you get 9. Add 1, you get 10. So we're going to go from 2 to 10. If you would like to rewrite this integral, you may pull that 3/2 in front, and then you'll write this as u to the 1/2 du. And then we'll integrate. This is much easier to integrate. But see how that was a kind of a process. We started out up over here, and we weren't quite sure what to do. We rewrote it as one fraction, split up the fraction into a radical over a radical, took the square root, did a u substitution. So there were a lot of steps, even though the steps themselves were not too crazy. There was still a lot to do. Okay, so I'm going to take 3/2 now. Increase the exponent by 1 and divide by the new exponent. And then you have 3/2 times 2/3 still gives you 1. So then you'll just have 10 to the 3/2 minus 2 to the 3/2. And whatever you do, please don't tell me this is 8 to the 3/2. You cannot do that. You cannot just like factor out the 10 minus 2 and take the quantity to the 3/2 power. Not equal to 8 to the 3/2. Don't do it. That's not an actual exponent rule. But what we can do is write the 3/2 power as 1.5. If you find that easier. I feel like this, at least when you see it, you kind of get a sense for like, okay, now I know I can't simplify any further. It's done. You don't have to write it in radical notation. You could always leave it with the rational exponent also. But that was an example of just an integral that you would have to work with that would be slightly more complicated. All right, I'm going to do one more. And we're going to use this concept again when we talk about surface area next week. But I want to do one more, and it's a specific type of integral. And then we'll be done. And if I end up owing you time, I'll give it back to you Wednesday. I don't know. We'll figure out how long this is when I upload it to YouTube. I'll try to limit the amount of yapping I do at the end. Example 3. Find the arc length of y equals x to the 4th over 4 plus 1 over 8x squared. And this is on the interval from 1 to 2. Now, this is a classic arc length problem you're going to see in every textbook for calculus in this world talking about arc length, this type of function. I'm going to show you how to work with this and how to use some algebra to manipulate this to get into the form that we're looking for. First of all, since you know you're going to have to take the derivative, you might want to rewrite y before you take the derivative, just to get it into a form that looks better for you. So like 1/8 x to the -2nd. Remember in Calc 1 when we spent all that time rewriting functions just so that we could take their derivatives? Well, you're doing that again. So y prime, well, 4 times 1/4 is 1. Decrease the power by 1. And then bring down the exponent. You'll get minus 1/4. Decrease the exponent by 1. And you'll get to the -3rd power. Now, if you'd like, you don't have to, but I think this will make it a little bit easier to see. Rewrite this so that you have this fractional notation still. Okay. So that's y prime. Now we're going to take y prime and we're going to square it. So back to our arc length formula here. I also feel like it might be easier for you to square when it's in this fractional form. I could be wrong, but it's probably easier to visualize. So we're going to FOIL this out. X cubed times x cubed. Remember, you're multiplying and you have the same base. You add the exponents. And then we have minus. Well, when I multiply the outsides together, the x cubes are going to cancel. So I have minus 1/4 and then minus 1/4 again, and then plus 1/16 x to the 6th. So this is really x to the 6th minus 1/2 plus 1 over 16x to the 6th power. Now, the next thing we're going to do is add 1, which is going to be trivial. So again, when we're writing this arc length formula, we're just building it up. We take the derivative, we square it, we add 1, then we square root it. Now, when I add 1 to this quantity, I'm not going to be affecting either one of these variable terms. I'm just going to be adding 1 to the constant term, essentially. -1/2 plus 1 is +1/2. So not much is really changing here, but it does matter. Okay, so 2 things you can do here. One of these things is to notice that these two are basically the exact same. The difference is the middle terms. One of them's positive, one of them's negative. You can work your way backwards and you can factor this into this form. I'm going to show you why you need to do this. If you're not sure, why would I factor and put this back into a squared form? Well, because think about what happens when you set up your integral. What you're looking for here is this. Now, this, without the square root, no big deal. We know how to integrate that. No big deal. Power rule. It's a very different situation when you put the radical on there. What our goal is here is to write the radicand as a quantity squared, because I know that if I take the square root of a quantity squared, it's like the square root and the square kind of cancel each other out, and I just have what's inside left over. Okay, so like I said, you can work your way backwards, or you can factor this using your special formula for perfect square trinomials. So I'm going to remind you of what that is. Because you actually have a perfect square trinomial, you just don't know it. So these are going to be of the form a squared plus 2ab plus b squared. They could be of the form also minus 2ab. In our case, we're dealing with a plus. We're always going to be dealing with a plus because we're going to always be adding one. So this is going to be a plus b quantity squared. You just need to verify that you have a perfect square trinomial if you're going to use this formula. So if we were matching this up here with what we have for our trinomial, I would say that a squared in our case is x to the 6th. And b squared in our case, this last term, is 1 over 16x to the 6th. So now we can write a and b on their own without their squares. And we'll verify we have a perfect square trinomial by just taking 2ab and verifying that we get 1/2. So a in this case is the square root of x to the 6th, which is x to the 6th to the 1/2 power. Take power to a power, you multiply the powers. 6 times 1/2 is 3. And do the same thing for b. Take the square root. The square root of 16 is 4. The square root of x to the 6th is x cubed. And then 2ab in this case would be twice, and then x cubed, and then 1 over 4x cubed. And then you would cancel out the x cubes, and 2 over 4 is indeed 1/2. So you do have a perfect square trinomial here, and the way you're going to factor that is like this. You're going to take a plus b quantity squared. So let's do that now. So we're going to rewrite our trinomial factored as a plus b quantity squared. Now, when we take the square root, we can easily integrate this because now we're noticing that we're taking the square root of a quantity that's squared. So we can rewrite the integral now as just the radicand. So get rid of the square and get rid of the square root. See how that works? Nothing too crazy, right? So I'm going to rewrite this just so that we can integrate it nicely using a negative exponent in the second term. And then we'll have 1/4 x to the 4th. Increase the exponent by 1. Your new exponent is going to be -2. So you're going to divide by the new exponent. So multiply by -1/2. And then we're going to evaluate this from 1 to 2. So we'll have 1/4 x to the 4th power minus 1/8. And then you can move that x squared into the denominator and go from 1 to 2. All right, so let's do that. 1/4 times 16 minus 1 over 8 times 4 minus 1/4 times 1 minus 1/8. Leave it like that. And you'll get 4 minus 1/32 minus 1/4 plus 1/8. Sorry. And then we'll just pop that into our calculator. 4 minus 1/32 minus 1/4 plus 1/8. And you will get 123 seconds. Okay, so that was kind of a process, but like I said, you're going to see this type of problem over and over and over again. So you're going to get used to doing that. Like I said, also, you don't have to continue verifying that you have this perfect square trinomial. You could have just worked your way backwards. Notice that this quantity right here, because we said the only difference between this guy and this one was just the sign on the 1/2. This one came from the minus variation. When you factor then the perfect square trinomial that you changed when you added 1 to it, you're basically just getting this square back. It's just going to have a plus sign instead of a minus sign in it. So I'm okay with you going from, I don't know, let's say from here to here. I'll tell you what students tend to do though. They notice, and you might have noticed this already because some of you will be pretty savvy. They're like, wait a second. This quantity right here at the bottom, 1/4 x to the 4th minus 1/8x squared, is almost exactly the same as what we started with. It's just a change in sign. That's going to happen with all of them. So you cannot just go from here to here. You got to show me some work in between. So I want to see you go through, take the derivative, square it, add 1 to it, and at this point, I want to see that you factored it at least. Put it in your integral and integrate. Or I think we're at the 2-hour mark. My goal here was to get enough done for tonight that you guys have enough to work on. I know you're going to be super busy already, but I want to keep test 1 where it is, just because I know we're going to need some time later. And if you feel kind of rushed right now, we're technically right on target. We're right where we should be. But if we have a little bit of extra time next week, as long as we don't move test 1, then we don't have to start anything from chapter 7. So if we're able to finish the material Wednesday, then I won't need to record an asynchronous lecture for you next week. I mean, we can add in an extra office hour or something, and you can just focus on learning what we've covered through Wednesday. Because I think I can technically finish this chapter out on Wednesday with just the surface area stuff in 6.5, adding that to some of the applications in 6.6. I don't have like a whole ton I want to do in 6.6, but I do want to kind of poke around and pick out some of those applications. So that's kind of my goal, is to finish the chapter with you Wednesday and then not assign you anything additional over the weekend. Just give you that week to prepare for your test that following Wednesday, which would be, wait for it, I have my schedule here. I was thinking about this a lot earlier. September 13th is the day that your test is scheduled. And I think we should be good for that. We're going to definitely need more time in chapter 7. So let's see how you're doing. Keep up with the homework. I'm going to put up some homework for 6.4. There isn't going to be a ton to do, but what is there is going to take you some time. And then some arc length problems from 6.5. Nothing super crazy, just some stuff here and there. Just basically covering the arc length topics that I just covered. Nothing too crazy. And that's it. So let me know if you have questions. Don't forget about the tutoring center. It's not that I don't want to answer your questions. It's just that I mean, think about the number of email questions I'm getting from students per day. And it takes a long time to sit there and leaf through your notes and try to figure out where you went wrong with something. And I don't always get to all of it just because it's a lot. Whereas the tutors, like that's their time that they're spending working anyway. Um, Use them. They're very, very helpful. Um, if you do have questions, yes, send them my way. If I can't get to like all of them right away, I'm sorry. I do the best that I can, but the tutors should be also a supplemental help source for you. Okay. All right. I'm gonna leave you on your own now so you can get started. And I hope that you have a wonderful weekend. Hopefully I'm catching you before the weekend hits. If you're watching this on Monday, I hope you had a wonderful weekend. And we'll finish off 6-5 and work on some 6-6 on Wednesday. All right. Adios.